All right. So you may be wondering about the exam and when I'm going to have that graded. I'm shooting for Thursday, but that may be a stretch, just looking at the schedule of things that I have and the available time, unfortunately, because we have labs this afternoon and on Wednesday afternoon, then that limits how much spare time I have to grade the exam. So I don't want to rush through doing those. I make every effort to understand the student solution and give you all the points that you potentially have coming to you. So I'll get that as quickly as I can. So looking at the future, we're now in chapter 4 of the textbook, and we're moving on to a new phase of the course where we start to talk about the movement of water. Till now, chapters 2 and 3 were focused exclusively on stationary fluids, and so we're looking at the hydrostatic equation, fluid properties, and those are really important foundational principles, but more often than not, what's interesting and applicable for engineers is the movement of water from one place to the other, or other fluids. And so that's what we'll start to get at now in chapter 4. The next homework assignment that you have on your plate, homework 5, that's posted now on Blackboard. You can get an early start on that today after some of the topics that we're going to be looking at, and then of course there's more problem solving related stuff that we'll get through on Thursday that ties into that homework assignment. All right, so are there any questions related to the course before we start talking about flow visualization and different types of flow? All right, if there are no questions, then let's move on. So far, like I just mentioned, it's been focusing on fluid properties and hydrostatics. But the movement of particles is important because there are a lot of applications like the movement of water through a pipe, or water flowing through a river, or hydraulic fluid inside of a transmission, or oil in an engine. So there's just a lot of applications where we have to be able to predict things about how quickly fluids are going to move, and as they move, how different properties associated with the fluids are changing. And so here's an aerial view and kind of a view of the spillway of a dam, just illustrating that, you know, the stakes are very high when you think about the number of people that are impacted by the existence of a dam and its potential for failure. The people who live downstream of a dam would be completely inundated in a lot of cases if the dam fails. And on the flip side of things, the benefits that can come to society from a hydropower generating dam and a flood control dam and a dam that makes rivers navigable and improves the transportation network of an area, there are really a lot of favorable benefits as well. And so understanding and harnessing the powers of fluid really is an important thing that will arise from our ability to predict things about the movement of fluids. Now there's a couple of different ways to handle the numerical complexity of predicting what will happen to fluids as they flow from place to place. And you may be wondering, what sorts of things are we interested to predict? And so, for instance, we may be interested to know what's going to be the velocity of a fluid as it moves from place to place. It could be the velocity of water in a river, and of course how steep the river is will be one factor that determines how quickly those water molecules are flowing through the river. But the grade of the stream isn't the only factor. There's also factors like what's the viscosity of the fluid, or what is the roughness of the stream. And so to answer questions like that, one of the numerical methods that we use is called the Lagrangian approach. And for that, it's pretty computationally intensive, because what we're attempting to do is track individual particles as they travel through space and time. And even if it's not every particle in a system, we may want to track the trajectory and the velocity and the characteristic of representative particles, so that if you follow 1,000 particles through a system and you see trends, then you can extrapolate those trends to the fluid more generally. And so in the Lagrangian approach, what we do is we would look at a fluid particle in 3 dimensions, and we would track its velocity in x, y, and z. And to understand its velocity in total, we would look at how over time, in an incrementally changing period of time, how its position changed in x, y, and z coordinates. And so the velocity at any given time is just going to be the velocity of each of its constituent directions. And the trick with this is, if you think about the time step may be very small, and so you may be looking at the movement of particles every second, or every 1/10 of a second, or every 100th of a second. And so to really understand what's happening inside of a system, you may have to have very, very small time intervals. And if you're tracking thousands or tens of thousands of particles, then keeping track of so many particles over time can really be quite a challenge. An impossibility on paper, and even a struggle with a high-power computer. And so to get around that complexity, a simplification to the Lagrangian approach is the Eulerian approach. And in the Eulerian approach, what we do is we divide up a flow field into windows or elements, or sometimes it's called a mesh. And so if you have a river and you divide it up into sections, then what you would do is you would look at fixed locations in space, those elements, and you would represent what's happening inside of that window by a single velocity, a single representative characteristic. And so the advantage of this approach is you can make the windows large or small depending on the computational power of the computer that's doing the modeling. But you would identify the velocity of a particle as it passes through the window, and then that represents all of the other particles inside of the window at that particular time. And so the way that we would determine the velocity is, again, in 3 dimensions. You'd look at the x, y, and z coordinates, and you'd look at the change in position over time, and then assign all of the particles inside the window. And so these 2 different approaches, the Lagrangian and the Eulerian, we will apply those different approaches when we are trying to predict things like what is the change in pressure that's caused by a change in velocity, or we may sometimes want to know what's the change in pressure when not necessarily the change in velocity with respect to time, but when the change in velocity with respect to position occurs. So we'll get into the details of both of those different cases, but the bottom line is that when a fluid's velocity is changing, its pressure changes as a result. And so we have to somehow predict how the fluid velocity is changing to understand what the pressure change would be in a pipe or around a wing, for example. All right, so let's take a look at this image. It's you can tell some sort of a model car inside of a wind tunnel. And what are some of the things that you can learn from this image? It's just a single moment in time, but can you tell which direction the wind is flowing from this image? What would you determine from the image? Is the wind going from the left to the right, or from the right to the left?
From the right to the left.
From the right to the left. That is correct. And what's the clue for that? How can you tell that the wind isn't going from the back of the car towards the front? Are there some visual clues that give you that idea? Okay, Dalton says which way the car is facing. Now, what do you suppose these white lines are? The path of the flow over the hood, it's breaking up on the left. All right. So Benjamin makes an important point. If you look at this, it's smoke that's being injected in the wind tunnel. And so there's a big fan not pictured. You know, off the screen to the right is a big fan, and it's blowing wind over the car. And so downstream of the fan is some sort of a smoke injection system. And the smoke is being used as a tracer to give you an idea, an indication of what's happening to the wind, because the wind itself is invisible. And so we need something to, a tracer, in order to make plain what's happening. Harrison says laminar to chaotic. So you can see that the effective diffusion hasn't yet occurred on the right side of the screen, because this smoke right now is kind of tight and continuous, but as it goes over the vehicle, it starts to disperse and spread out. The smoke molecules are diffusing and mixing with the surrounding air, and so the border becomes less distinct. We can still see that there seems to be like streaks of the smoke, but it's more faded because it's mixing with the surrounding air. And so that is just a visual clue that we can kind of tell that it's moving from the right to the left. But there are other things that we can also infer from the appearance of that smoke. And one is that the velocity is increasing as the wind encounters this passenger compartment. One thing that that we'll be talking about, these lines are called streak lines, and the streak lines, when they get closer together, the velocity is increasing. And so this passenger compartment is kind of deflecting the air out of the way, and so you have more air in a smaller amount of space. Like if you think about, the fan is blowing the wind through the entire wind tunnel, but now here you have an obstacle in the path of some of the wind. And so the wind that's coming up over the vehicle has to speed up, because it has a smaller cross-sectional area for that same mass of air to pass through. And so whereas it has a relatively large cross-sectional area here before it encounters the vehicle, when it gets to the passenger compartment, there's a smaller cross-sectional area, so the velocity is going up. So it makes sense conceptually why the velocity would be going up, but then we also have this visual representation. All right. Now streamlines are things that represent the velocity vector. They indicate the direction of flow. And here we have two different illustrations. On the left is an open channel, and the clues that we have that this is an open channel, meaning like a river flowing downhill. These little hashed black lines indicate that it's open to the atmosphere, and there's no line on top like there is on the right. On the right, this is indicating that it's a pipe, and so what we have is maybe a cross-sectional view of water flowing through a pipe. So open channel, closed conduit, meaning closed channel, and what these streamlines tell us is the direction of the velocity, but not necessarily the magnitude. We can't tell, for instance, in this pipe whether the velocity is going 1 meter per second or 10 meters per second. And similarly, the streamlines only give the idea of the direction, but we can't tell by looking at the streamlines whether the velocity at the center of the pipe is a lot faster than it is at the edge of the pipe. Conceptually, we think that's the case because of the effect of pipe friction, but the streamlines don't give an idea of magnitude, only the direction. So here's some other ways that streamlines can be used to help visualize flow. In the case of water that's emptying from a tank and then it's discharging through an orifice, you can see that the water is going down through the tank and it's discharging out into the air. And so these light blue streamlines give us an idea of the path that water would take if it followed that velocity vector. And so at any particular moment in time, you can see here A, B, and C, then that is the direction of the velocity at that moment. And so this particle that's here at A is going to change its direction in order to come out of the orifice, but at this particular moment, that arrow is showing you the direction of the velocity. Now, in the case of the streamline that's encountering an airfoil, there's this one streamline that dead ends, and it stops at the leading edge of the airfoil. And that stagnation point is going to be a location where the pressure increases slightly along the leading edge of the wing, because whenever you have velocity vector that just stops, then all of the energy that existed as velocity is being transferred into an increase in pressure. And so that's what happens on the leading edge of the wing. Streamlines can give you a relative idea of how the velocity vector is changing in this converging section, where you have a pipe and the diameter is getting narrower and narrower. What's happening is the streamlines are getting closer together, and that tells you that the velocity is increasing as they get closer together. And anytime the velocity vector is curved, then of course the magnitude of the velocity may not be changing, but its direction is changing. And velocity is a vector, meaning it has two components, the magnitude and the direction. And so if either one of them is changing, then an acceleration is required to cause that. And so in this converging section, there's an acceleration because the fluid is going from relatively slow on the left side, and it's speeding up to much greater on the right side. But then the acceleration that's occurring in this circular flow, water circulating, and the rotational flow that occurs there, it may have the same speed as the velocity vector circles around, but because the direction is changing, it would require an acceleration as well. Okay, so these are streamlines, and there are different types of flow that we can diagnose and determine by looking at the streamlines. And so if the streamlines are straight and parallel, like pictured here, then that tells us that the flow is uniform. Uniform is one of the first flow classifications we're going to talk about. And uniform means that the velocity is not changing with respect to position. That the velocity, direction, and magnitude are the same as it flows from left to right. So here it's saying that the change in velocity with respect to position is 0. The flip side of that, the opposite of uniform flow, is non-uniform flow. And that is when the velocity is changing as the fluid goes along the direction indicated by the streamline. And so if the streamlines are curved or not parallel, then this is a representation of non-uniform flow. And so the velocity is getting faster as you move from left to right. So that's non-uniform because the velocity went up. Or if the direction of the velocity changes, then that's also non-uniform flow. Okay, so steady versus unsteady is going to be the next way that we classify flow. Uniform, non-uniform is the first way that we classify flow, and so that's all about position. Is the velocity changing with respect to position? Steady versus unsteady is about time. And so steady flow means that the velocity is being constant during some period of time. So the velocity isn't changing during that increment. Unsteady flow means that the velocity is changing during a time interval. And we can't look at just a single picture and determine whether conditions are steady or unsteady. We can use a picture to tell us whether it's uniform or not uniform, but it requires a video or a series of images over some period of time to tell us whether the flow conditions are steady or unsteady. So, that's why, a photograph just represents what's happening at an instant rather than a period of time. All right, so let's take a quick look at unsteady flow here. Let me get this video. All right. All right, so what we're going to look at there. So what happened was these guys were on a hike and it started raining in the watershed upstream that contributes to the stream bed that they're climbing through. And so, in the beginning, we just see a dry riverbed, and they can kind of hear something in the distance. You can tell it's a cloudy day here. They can hear in the distance the approaching wave of water. And so the before, when there's no water, and then the after, when it's flowing so quickly that it could sweep you off your feet and throw you into a rock and hold you under the water. And these are really dangerous, these flash floods. This is a good illustration of how we can use a video segment just to illustrate that unsteady flow is when the flow conditions are changing in a period of time. By the way, if you're interested in understanding about flash floods and how to do calculations related to how much water there will be for a certain watershed area, I teach a course called Hydrology. It's Civil Engineering 433, where we do a lot of work related to flash flooding and modeling and prediction and that sort of thing. Okay. So the two different types of flow conditions we've talked about so far are steady versus unsteady, uniform versus non-uniform, and another way to classify flow is by whether the conditions are laminar or turbulent. And so laminar conditions is associated with slow-moving flow, where the water is flowing in a very orderly way, and so it has a smooth appearance. And it's common in viscous fluids like syrup or honey. You can have laminar flow with water, but the velocity has to be really low, or you have to pay special attention to not disturbing the stream. There are a couple of really interesting YouTube videos out there about people who create laminar flow water features. And if you've ever been to the Detroit airport and walked around inside the terminal building, maybe you've seen that they have these jets of water that kind of dance from pool to pool, and that's another illustration of laminar flow conditions. Typically, laminar flow conditions have a Reynolds number of less than 2,000. And so RE stands for Reynolds number. And the formula for the Reynolds number is that if you have water flowing through a pipe, then you would, or any fluid, you would take the density of that fluid, its velocity, multiply it by the diameter, and then divide by the viscosity. And so you would get some unitless number. The units cancel out here on the right side of the Reynolds number equation. And then if the Reynolds number is less than 2,000, then conditions are most likely laminar inside of that pipe. The flip side of that is turbulent flow. And so turbulent flow is characteristic of fast-moving liquids with a lot of mixing. And so if water is flowing through a pipe at a high velocity, then probably the conditions inside of that pipe are turbulent. And so rather than this nice smooth velocity profile that we can see in the case of laminar flow, where in laminar flow the velocity is faster at the center of the pipe than it is at the edge, because at the edge of the pipe the water is experiencing some pipe friction, and that reduces the velocity. And there's just a really gradual transition from the zero velocity water that's at the boundary of the pipe and the liquid, and then the further away you get from the edge where the pipe friction is being applied, then the velocity increases, and this has kind of a parabolic shape to it. In the case of turbulent flow, though, there's so much random movement and mixing that rather than a nice smooth velocity profile, it's kind of jagged and uneven and turbulent. So that is with a Reynolds number greater than 4,000. And so there's kind of a middle zone between 2,000 and 4,000. We call it transition flow. And transition flow sometimes is laminar, sometimes is turbulent. It depends on the circumstances, and it depends on whether the flow before you got into the transition zone had been laminar or turbulent. So if you were gradually increasing the flow rate through a pipe and it started off as laminar, then it may stay laminar in through the transition zone for a while. And if you were decreasing the flow rate through a pipe and it had been turbulent because you had a really high velocity, but then you're closing the valve and slowing down the water velocity, then it may stay turbulent until you get down below 2000. All right, so just to get some practice with this Reynolds number equation, here this example poses the question, what would be the Reynolds number if you have a flow velocity of 0.1 meters per second of water going through a 2.5 meter diameter pipe? And then part B, what's the maximum flow velocity for the pipe which will allow you to have laminar flow? So you're solving for V with a Reynolds number of 2000. Now, not on the screen is the viscosity and the density. And I usually write that on the whiteboard, but let me just type it on here for you so that you've got that available as you work through the example. The density of water, of course, is 1,000 kilograms per cubic meter, and the viscosity is 1 times 10 to the minus 3 newtons seconds per meter squared. All right, so let me pause for a moment as you try and determine what is the Reynolds number for the circumstances that are described here, where you have a velocity of 0.1 meter per second and the pipe diameter is 2.5 meters. All right, so for a velocity of 0.1 meters per second and water viscosity. Now, remember that there's two ways to describe viscosity. One is by the absolute viscosity, and one is with the kinematic viscosity. And so the Reynolds number can be expressed two different ways. It can be expressed density times velocity times diameter divided by the absolute viscosity. And so that's probably, that's what I had on the screen just a moment ago. But another way to do it is velocity times diameter divided by kinematic viscosity. And remember, the definition of kinematic viscosity is absolute viscosity divided by density. So I sometimes just jump straight to the shortcut of Reynolds number is V times D divided by kinematic viscosity. And you can see here I've said the kinematic viscosity is absolute divided by density. And so on the previous slide, if you have 1 times 10 to the minus third divided by 1,000, then it gives you 1 times 10 to the minus sixth. In the end, you'll get the same answer either way. You'll get that the Reynolds number is 250,000. Any questions about that first part? All right. Now, for part B, what is the maximum velocity where you will still have laminar flow? And so what we're doing for that one is use this formula and set Reynolds number to 2,000. Viscosity is still 1 times 10 to the minus 3. Density is still 1,000. The pipe diameter is still 2.5 meters, but we're solving for velocity. So what velocity can we have and have the Reynolds number less than 2,000? So has anybody calculated part B yet? When you do, please put that in the text area there, in the chat. All right, so we say if we want to see laminar behavior, how slow is the velocity going to need to be? And since this is such a large diameter pipe, it turns out that it is indeed going to have to be a very, very low velocity. 0.8 millimeters per second. Now, for those of you who are the civil engineering students that will be in the lab, today and tomorrow, we're actually going to see laminar flow and turbulent flow. We'll be doing a demonstration and an experiment during today's lab where we visualize laminar flow. And so we'll have a much smaller diameter tube. We'll have a viewing tube that has a diameter of 1 centimeter. And with that, it'll allow us to have a slightly higher velocity than in this example. But we'll be doing the same thing. We'll be trying to see what velocity is associated with, obviously, laminar flow conditions. All right, so any questions about this illustration and example? Joseph, do you have a question?
No, I don't. That was by accident.
Okay. So just to summarize, we are going to build out a table that compares different flow classifications. And what we've seen so far is that flow can be classified as either non-uniform or uniform, and that has to do with position. And flow can be steady or unsteady. And you can have any combination of those two. For example, you can have uniform flow that is steady. And you can also have uniform flow that is unsteady. And you can have unsteady, non-uniform flow. So it's a 2x2 matrix there. What we'll learn is that when the velocity changes with respect to position, then that's one different type of acceleration compared to when the velocity changes with respect to time. And those different acceleration types are going to cause different effects in the fluid. And so we'll revisit this particular slide and build it out with other information in future lectures. All right, so a streamline is showing the direction of the velocity, but it doesn't tell us the magnitude directly. There is a way for us to figure out the magnitude of the velocity, and that is if you connect the dots for the path that a particle has taken over time. That path line would show you how the particle is moving over a period and how far apart the particle is moving, like let's say for example every 1 second. If it's moving a big distance in those 1 second intervals, then that would give you an indicator that the velocity was high. And so that's what a path line is. The third type of flow visualization is a streamline. And if you continuously inject a dye or a smoke tracer at a fixed point in space, then the streamline can be used to tell you the history of flow during that period. So path lines and streamlines may seem like they're pretty similar, but I'll try and illustrate how they're different and how we can use them to give us information about what the fluid is doing. So in this scenario, we're going to open up that attachment in just a minute. So if you have that PDF file that I emailed to you at the beginning of class, have that at the ready. But before we get to that, here's the scenario. There is a period of time, T0, when the flow direction changed. And before T0, the flow was going from the left towards the right. So it was flowing in the direction indicated by the arrow. But then after that time period, the water changed direction. So now it's changing and it's flowing upward and to the right. And so with that said, here is this is a figure that's taken from the book. So this is before the time on the left. So when the water was flowing just from the left to the right, then the particle was flowing. You can see these black dots just indicate what direction the particle, how it moved. And so it started here at this location, and then it got pushed to the right by the flowing fluid. But then after T0, remember at T0 the flow direction changed, and so the particle got moved. So these dotted lines, each of these dots just shows you where the particle was at a certain time. And so then it changed direction, and the particle got moved upward and to the right. And so the blue lines are the streamlines, and it's kind of a pity that they drew them on top of each other, but you know, the illustration is what it is. It's flowing to the right before this instant in time, and then upward and to the right after. And so you can see what the path line shows you. This is the path line. Now, the streak line is a little bit different, because in the case of the streak line, what's happening is here at the starting point, think that's where we're starting to inject a dye. Or think about if you had a can of paint in your hands and you were pouring the paint into the water, then what would happen is that the paint would get pushed to the right by the flow. But then if all of the flow suddenly changed direction, then this paint here is what you poured in initially. Like the very first molecule of paint that you poured in is here at the end. It's at the tip of this, because we were always pouring the paint at a certain fixed location in space. And so that first molecule of paint right here got pushed to the right, but then this entire line is shifted upward when the flow direction changes up and to the right after a certain time. So that's a streak line. And I know it may look that a streak line is just only always the inverse of a path line, but it's not quite as simple as that. It's not always just going to be a reflection, the streak line being a reflection of the path line. There's a little bit more to it than that. And so what I'd like to show you is how you can draw the path line and the streak line when you're given a streamline. Okay, so now we will get to that handout. Here's the scenario, is that here is a certain location in space that we're going to start with. And let's say that there is some sort of like a floating can in the water. And right now, at this instant in time, the water isn't moving. And so this can is just going to stay where it is. But then the water is going to start flowing to the right for 9 seconds. And so if the water is flowing to the right, then that's going to change the location of the can. And if the water is going at the same velocity during each of these time intervals, like if we say it's just moving 1 square during each second, then it'll be pretty straightforward to draw the path line. You just basically track where the particle is getting pushed around to. And so the tip here is you just follow the object as it moves. But then in the case of the streak line, what's easier to do if you want to draw the streak line, let me open up that handout that I gave you. Let's see. Here it is. All right, so the direction that the water is going to move is going to be to the right, down, and then to the left. And so let me show you what the path line and the streak line look like. Here we go. All right, this is the one. So the path line starts here at the origin, and you can see that in the 9-second interval that the water is flowing to the right, we've moved 1, 2, 3, 4, 5, 6, 7, 8, 9 units to the right. And so the path line is just the can is floating, and then it goes down. And so it was a 4-second interval that it's moving down. So 1, 2, 3, 4, and then it flowed to the right 6 seconds, and so 1, 2, 3, 4, 5, 6. So this was the starting location and then the end. The thing to do to draw a streak line is to hold your pencil or your pen steady and to move the paper in the direction indicated by the arrows. And so For example, if I put my finger on the screen and then I started moving the screen in the direction indicated by the arrows, and for that duration, then it would draw the streak line out. And so I'm holding my finger steady and then I'm moving the paper to the right, and then I'm moving the paper down, and then I'm moving the paper to the left. And so what that will look like is, here is the first location where I started to inject the dye, or this is like the first place that my pen was, but I'm moving the paper in the direction of the flow. And so if I'm moving the paper to the right, then it makes this horizontal line. And you can see that it's 9 units long because I was moving the paper to the right for 9 units. And so this is the starting point, and then this is the end of those 9 units. And then I moved the paper down. And if I'm moving the paper down, then that effectively is the same as moving my pencil up. And so the flow field is going downward, then the streak line is going upward, and this first line is shifted down because of the movement of the flow field. And then the flow field in the last segment is going to the left for 6 seconds, and so everything is shifted to the left, and then this is like the very last element of fluid that gets into the water. I know it's a little bit strange to think of it that way, but that's how it goes. And so if you have already printed out that PDF file that I sent you at the beginning of class, then let's take a look at this example. And if you haven't, then you can just do it on a scratch paper there in front of you. But the first question asks, if the water is moving to the right for 3 seconds, down from seconds 3 through 5, and so that's a 2-second interval, through 5 through 9, it's down and to the left, and then it's to the right from 9 to 11. And anytime it's going at an angle, you'll see here that what I'm suggesting is that we assume that the velocity is now 1.41 times faster. And so it's just always going to end up right at the intersection of those guiding dashed lines. So what I'd like you to do is draw just the path line. And so try and figure out, if this object at A gets pushed around by the fluid in the direction indicated by those streamlines, then what kind of a path line would be generated? All right, let me pull that solution up just to see if you were thinking in the right way. All right. So the object that's at A got pushed 1, 2, 3 units to the right. Then it got pushed 2 units down from 5 through 9, so 5, 6, 7, 8, 9, down and to the left, and then 2 units to the right, 1, 2. So it's relatively easy to draw the path lines. In the second part of this example, though, it's asking you to draw the streak line. And so I give you the 2 different pieces of the 2 segments here, because the suggestion is first sketch out the shape of the streak line, and then you have to transpose it into the correct location. So the problem scenario is that we're always going to be injecting a tracer at B, and then the water is going to be flowing according to these directions that are indicated by the streamlines. And so it's going to be the same 3 seconds to the right, 2 seconds of movement downwards, and so on. So you move the paper in the manner directed by these streamlines and come up with the shape of the streakline, and then you transpose that shape of the streakline into the correct location, because it has to end, the very end of the tip needs to be at location B. So let me just give you a moment to try and sketch something out, and then I'll show you what the streakline looks like and where it should be located. All right, so let me zoom out so that we can see the streamlines as we look at the streakline. All right, so here is where I just first of all got the shape of what the streakline should look like. And so I just started at some particular location and I moved the paper to the right. And so this is where I first started. I put my pencil down and I started moving the paper to the right. And so the line is to the left because I was moving the paper in the direction of the flow field. And then this next vertical line here, it's a line upward because I was moving the paper down during the second interval. And then this angled section here, I'm moving the paper down and to the left, and so that essentially means that the streakline is going up and to the right. And then finally I move the paper to the right, and then that makes this line that's going to the left. And so this is where my pencil started. This was the last part that I drew. And what I know is that if the scenario is that I was always injecting that dye at location B, then this has to end, the line has to end at B. And so I had to use the scratch paper because I didn't necessarily know where the line was going to end. And so I get the shape of it, a scaled shape, and then I just sketch it out, transpose it onto the graph on the left. So, you know, this is awkward at first when you first begin to do it, but it's not especially mentally rigorous. It's just the sort of thing that you need a little bit of practice with. So you will get some of that practice in the homework assignment. By the way, here's the homework assignment that's posted online now. And so the first two questions, well, not the first two, question 1 and question 3 have some flow visualization application that's related to this material. All right, so let's talk about a couple of different acceleration types. Remember, we have uniform flow, which means that it's not changing with respect to position. And then there's steady flow, which means that the flow isn't changing with respect to time. But sometimes fluids are going to be changing with respect to time and position. And so the acceleration is what causes those changes. And acceleration that changes with respect to time, where the velocity is increasing with respect to time. Let me show you this quick little video here of a rocket sled. Let me pause the YouTube recording. YouTube doesn't like it when you record YouTube. Like I said before, is that you can have simultaneously the velocity changing with respect to time and position. And so the time-dependent change in velocity is the tangential acceleration, which is related to a change in speed. The centripetal acceleration is normal to the path line, and it's position dependent. So local acceleration was that rocket sled, where we have unsteady conditions and over time the velocity is increasing. Convective acceleration is when the flow is non-uniform. And so you can see in this nozzle that on the left side of the nozzle, where the diameter of the opening is relatively large, that the velocity is 10 meters per second. But then what's happening is that the diameter of the nozzle is decreasing, and that's forcing the velocity to increase, and so the water comes out of the nozzle at a faster velocity than it entered the nozzle. And so that's an illustration of a convective acceleration where even if the conditions are steady, meaning that the velocity doesn't change over time, it's the same flow rate going into this nozzle now as in 10 minutes from now, but because of the changing shape, then that accelerates the fluid with respect to its position. So these are two different types of acceleration, local and convective, that have two different effects on the fluid. And so we're going to use one equation for predicting what happens to the fluid pressure when it experiences a local acceleration, and a different equation that predicts what happens to the fluid pressure when you have convective acceleration. So we're filling out that same table that I showed you earlier. Uniform versus non-uniform is all about the change in position. And non-uniform flow occurs because of convective acceleration, whereas unsteady flow occurs because of local acceleration. All right, that's all I have for you today. Remember that if you've got lab today, the schedule of who comes at 2 and who comes at 3 is posted online. I'm going to get onto those exams and get them back to you as soon as I can, but if you have any other questions in the meantime, feel free to reach out on Teams and I'd be glad to talk to you. The homework number 5 is available now if you want to get a start on that flow visualization and streamline, pathline type stuff. It's available now. That's it for today. I'll see you on Thursday.